Let us continue our discussion that we started in the last lecture. In the last lecture, we discussed several aspects of molecular dynamics and we ended the last lecture with this particular slide which talks of the equations of motion. So, the top line shows the Newton's equations of motion and this force is nothing but gradient of the potential. What is the meaning of gradient? You plot the potential along a distance and take the slope along that direction. So, that is my force. Force is the gradient of the potential and is the formula for the force. And to find this formula for the force, you need that model for the potential. In this case, the model for potential was the Lennard-Jones potential. So, this would be the force between any two particles I and j, okay, I and j. So, now suppose we consider the whole system. So, next slide, this shows my system. So, my original system consists of only 4 particles, it could be 4, it could be 4000, but each of this box is surrounded by similar boxes on all sides. Now, why do I surround this box on all sides by similar boxes? Because if I continue this repetition in all directions, so I have an infinite system. So, an infinite system will really behave like a liquid, not like just a box. So, that is what is the meaning of periodic boundary condition. The meaning of periodic boundary condition is that whatever happens in this central box is repeated in all other boxes. See, for example, suppose this molecule here moves into this box. So, if this molecule moves in this box, this molecule moves in the box to the next side. Okay. So, if one molecule moves to the box to the right, another molecule will move to the box to the original box. So, what periodic boundary conditions guarantee is that the density of my system will not change. So, periodic boundary condition ensures that the density will not change, and in addition to that, what we do is called a minimum image convention. So, before I go to this minimum image convention, so let us understand this properly again. Each box is surrounded on all sides by boxes of a similar type. So, in 2 dimensions, it will be surrounded by 8 boxes. What are those 8 boxes? 1, 2, 3, 4, 5, 6, 7, 8. So, in 2 dimension, each box is surrounded by 8 boxes. In 3 dimensions, the central box will be surrounded by 27 boxes, 26 boxes. Make sure you get this right, because not only there will be these 8, there will be 9 boxes behind this screen and there will be 9 boxes in front of the screen. So, 9 plus 9, that is 18, plus these 8. So, there will be 26 boxes surrounding this central box. So, that is my periodic boundary condition, and the advantage of periodic boundary condition is that each particle in my periodic system will interact with all the particles around itself. Okay. So, this is called a minimum image convention. So, what is the meaning of a minimum image convention? Each particle interacts with all its neighbors in such a way that this particle is treated as the center of the box. So, for example, if this molecule is the end of this box, it will not interact with molecule J in the same box, it will interact with molecule J prime, because that J prime is closer to I than J. So, that is the meaning of minimum image convention. Minimum image means around each particle I construct a box of the same size as the original box, and the particle will interact with all the particles in that box with this particle as the center. So, what it means for particle I, in this case I will use Rij prime and not Rij. Okay. So, when I do a computer program, how will I know whether I should calculate J prime or J? So, this is an algorithm for that. Okay. This is an algorithm. So, that algorithm says Xij, that is the distance between I and j, will be actual Xij. Okay. So, this is the original Xij minus box length times nint Xij by L. Xij is this distance and L is the box length. So, when I divide Xij by L, so I get an integer. So, if I take the integer part of that and multiply by L, I will get the real Xij. So, what is nint A? Nearest integer to A. So, nearest integer to A. For example, this if Xij is more than the half box length, suppose Xij is 0.7 times L. So, then the integer is 1. So, if this Xij is 0.7 times L, so I will not take the original Xij, but I will subtract that L because now it has become 1. So, I will take xij prime. So, this ensures that I interact with only those particles which are within the half box length about this particle. Okay. So, the same thing is illustrated here. Okay. Same thing is illustrated here. I have a particle in this box. So, this will not interact with any particle outside that cut. Cut means the L by 2 is a cutoff length. All molecules whose length is more than L by 2 are not considered at all. Okay. So, that is the meaning of saying that each molecule is treated as the center of the box in which it is located. So, each molecule behaves as if it is in the center of that box. So, and the great advantage is that the boundary effects are taken care. So, suppose I did not have periodic boundary conditions. If I did not have periodic boundary conditions, this particle will interact only with these particles and this will behave as if it is in the edge of the box. Whereas, if I have periodic boundary condition, there is no edge anymore. Each particle is surrounded by a similar box around itself. So, the edge effects are gone. So, it is a very standard practice to do molecular dynamics with periodic boundary conditions and minimum image convention. The only problem would be if they are Coulombic interactions, this situation is not adequate, because in a Coulombic situation there are long range interactions. So, therefore, I have to consider things like Ewald sum or reaction field. I have already mentioned this in my last class, and when you do GROMAC simulations, you will have more occasion to use these particular ways of doing things. So, now let us do this integration algorithm. What is an integration algorithm? I have a position r, and in the next, suppose I have a time step. In all our simulations, delta t will be the time step. So, after this time delta t, where will the particle be located? So, to find that out, the particle will be acted upon by velocity as well as the acceleration. So, the new position will be velocity into delta t. So, this is by the velocity term, okay, and this is due to the acceleration term. Okay, this is the acceleration term. So, the net displacement would be a sum of velocity term and the acceleration term. So, the new position will be r at t plus delta t. So, that is how I have to do my simulations. I have original position r, original position t, original force f of t at this particular position. So, when I calculate the new position, okay, I have calculated the new position by adding these two components to the movement. So, that is my new position. Now, how do I determine velocity? So, that is the question now. How do I determine velocity? That is the challenge. Then once I have the new position, in that new position there will be new force. So, what will be the new force at this point? I need the new velocity, which is already given here. I have to calculate the new force, then I will have the new position from this. So, if I keep on going from one position to the next position to the other one, so that constitutes the trajectory. Trajectory means all the positions in a sequence, that is my trajectory. Okay. So, as I mentioned, how to calculate velocity. So, that is a slightly tricky. So, one of the oldest and the most used algorithm is called a Verlet algorithm. So, let me describe here the steps of a Verlet algorithm. So, what is done in Verlet algorithm? I do a Taylor expansion of it should be of, not OR, Taylor expansion of r at t plus delta t in terms of RT. So, I want to do a Taylor expansion, new position in terms of old position. So, how do I do the Taylor expansion? R at new position will be r at the current position plus r dot t, this should be r dot t, I do not know whether that dot is available. Okay. So, this should be okay. So, this should be new position plus velocity times delta t plus acceleration times delta t square plus third derivative into delta t cubed and so on. So, remember that this is the velocity, not r, this is acceleration. Okay. So, this is r at t plus delta t. At t minus delta t, it will be r t minus velocity into delta t plus acceleration into delta t square minus third derivative of r into delta t cubed and so on. So, this is the new position, this is the old position. If I add the two, what I get is r at t plus delta t plus r at t minus delta t is 2 r t plus, this should be force into delta t square. There should be r double dot t into delta t square plus order t fourth, or the new position is given by 2 times the old position minus the one position before the old position t minus delta t plus force into delta t square. So, remember this r, it should be r double dot t. So, that is force into delta t square by m. Okay. So, that is the acceleration into plus a correction of the fourth order. So, this particular algorithm, so this is our main result here. The new position is given in terms of 2 times the current position minus the old position plus acceleration into delta t square, okay, plus a correction term. So, now just I got the new position, I can also get velocity now. How do I get velocity? I subtract 2 from 1. When I subtract, new position minus the previous position will be 2 times, this should be again velocity into delta t plus a correction. So, the velocity now will be r at t plus delta t minus r at t minus delta t divided by 2 delta t. It is really like a change in position in 2 steps divided by the time for 2 steps. So, that is my velocity. So, the only problem of this is that I can get the new position in terms of the old position, but I cannot get the new velocity. What I got really is the current velocity, because this velocity is now at the current position and not the new position. So, that is the problem. But when we need only forces, suppose I need forces, in terms of that force I have the new position. If I do not need velocity for any specific purpose, this is an OK algorithm. Now, there is also a refined algorithm for this, it is called the velocity Worley algorithm. I urge you to look it up in the websites. So, that is more symmetric with respect to position and velocities. This is not symmetric between position and velocities, because new position is predicted in terms of old positions, okay, whereas there is no formula for new velocity. So, that is the lacuna here, but it does not matter, because many times we just want new positions as a function of time. I also get new velocity when I reach the new position. For the new velocity I can always get after I have gone to the new position, I can get this in the next step. So, in principle I have velocities at each step and positions at each step. Okay. So, now just as I described the Worley algorithm, there is another algorithm called the predictor corrector. So, this is a slightly improved algorithm. Okay. So, there are many algorithms here. So, I will just discuss 2 so that you know that there is no unique algorithm here. And what was good thing about Worley algorithm? The corrections to positions, look at here, the corrections position to position is the 4th order. So, if your delta t was 0.1, delta t to the 4 will be 0.0001. So, the corrections are to the 4th order, there is no correction to the 3rd order, whereas for velocity there is correction to the 2nd order. So, now coming to the predictor corrector, I have initial position, initial velocity, I calculate the initial acceleration. How do I calculate the initial acceleration? Calculate the force divided by mass, that is my initial acceleration. So, once I know the initial acceleration, I can predict new position and new velocity using a Taylor series. Okay. Here there are no corrections in the slide. In the previous slide, I did not write velocities and acceleration properly. This is better here. Predicted position at t plus delta t, current position plus velocity into delta t plus acceleration by t into delta t square. So, this is my predicted position, this is my predicted velocity at t plus delta t is, at t plus delta t is the current new velocity is current velocity plus acceleration into delta t. What is the predicted acceleration? Present acceleration plus 3rd derivative into delta t. So, to get the new acceleration, I need the 3rd derivative of position with respect to time. So, velocity is the first derivative, acceleration is the second derivative, the 3rd derivative of r, normally we do not use it. So, we do not come across. So, here to know the new acceleration, I need the 3rd derivative of r with respect to t. So, these are my predicted position. How do I correct them? To correct them, I calculate a correction. So, corrected acceleration is force at the new predicted position divided by mass. Okay. This is my correction. So, what is a change in the acceleration now? Corrected acceleration minus the predicted acceleration. Okay. So, this is my correction. So, how do I correct positions now? The corrected position is predicted position plus a constant times delta t square by 2 into correction in acceleration. Corrected velocity will be predicted velocity plus a constant times delta t into some correction in acceleration. So, these constants will now determine the accuracy. So, there are ways to determine these constants. So, one can do the predicted corrected algorithm. Okay. So, now so far we have told you how to do the dynamics, but when I am starting my simulation, that is initial step, how will I know the velocities? Okay. So, I do not know my velocities when I start my simulation. So, one way to get those velocities is through a Maxwell-Boltzmann distribution. So, remember we studied our random numbers. One of the greatest application of random numbers is to calculate these velocities. How do I determine these velocities? You know that they are distributed according to a Maxwell-Boltzmann distribution. So, I determine the velocities in this manner using Gaussian random numbers, and once I obtain these velocities, I determine the temperature to those velocities. How do I determine the temperature? You know that when I take the average of kinetic energy, so the average kinetic energy is nothing but 3 by 2 kT. So, that is the equipartition theorem. So, I determine a set of velocities, I determine the average kinetic energy and equate it to 3 by 2 kT. So, if the average kinetic energy is not equal to 3 by 2, if it is less, I increase all the velocities such that I get the average temperature. So, when you do a simulation, you want to do the simulation at a given temperature, and you can obtain a Gaussian distribution at that temperature and assign all the initial velocities. Okay. So, now let us come to the basic algorithm of this molecular dynamics. So, we know now the equations of motion, okay. We know the algorithm. So, now we are in a good position to study the structure of this program. So, how does this program work now? Set initial conditions, that is I determine all the initial positions and all the velocities. So, these velocities could be through the Maxwell-Boltzmann distribution, or if you have already done the simulation earlier. So, at the end of the simulation you will have some velocity. So, I can use the last point of the previous simulation as the starting point for the new simulation. We will do this through a practical session as well. So, set up the initial conditions, calculate the new forces. So, once you calculate the new forces, solve the equations of motion. Okay. We have chosen a time step. Once you have chosen its time steps, you have new position, and new velocity after a time step delta t. So, once you do that, you increment the time again. So, I determined at a new time step. So, now I want to increment time further. So, how long will I increment the time? Suppose I want to do a simulation for 100 picoseconds. So, if my time has been incremented, because I did a simulation for delta t. So, now t has become incremented by delta t. So, if this time is greater than the maximum time that I want to simulate, such as 100 nanosecond, if it is greater, then I stop. So, if it is less, I go back, calculate new forces, calculate new velocities, new positions, and keep on repeating the simulation. Okay. So, once I reach a time step which is the maximum time, I conclude my simulation. So, that is the same thing written on the right side. Set up the initial system, calculate the forces on all sides, calculate new site positions and velocities, repeat for n steps. This n will be determined by the maximum time T max. Calculate the physical properties, and the other thing is you have to check for convergence. So, we will have more to discuss on convergence, because one of the very important ideas in simulations is that all the results you do should converge to a given value, because if they do not converge, there is no meaning in this simulation. So, I shall discuss that as we go along. So, the next thing I want to comment, what time step do I use for molecular dynamics? Okay. So, if I use a very large time step, okay, then energy is not conserved. There will be problems, because particles will start moving too fast, they approach other particles, then there will be lot of problems with conserving energy. Okay. So, a standard practice will be that delta r by delta t should be 1 by 20th of the nearest atom distance. So, there are distances between atoms. So, typically they are 3 angstroms. So, velocity should be typically 1 by delta r by delta t should, if it is typically less than 1 by 20 in magnitude, then that is a good time step. So, typically in practice delta t of less than 4 femtosecond is very good. Femtosecond is 10 minus 15 seconds. So, ideally one uses around 0.1 femtosecond or 2 femtosecond. These are very good time steps. for complex molecules. For very simple molecules, you may even use up to 5 femtoseconds. So, this is the time step, and nowadays because we have fairly good and fast computers, molecular dynamics is done for about 100 nanosecond. Remember, I had a T max in the last slide. Typically, one does simulations for 100 nanoseconds to get convergence. Okay. So, now when we do simulations, another thing that is important is temperature control. Okay. Usually, this is not necessary, but it is always a good idea to rescale velocities to the target velocity every now and then. Okay. So, this when you do rescaling, it makes the system a lot stabler. Okay. Ideally, in molecular dynamics, one should not do rescaling, but if you do not do rescaling, many times there will be a problem. So, if you do rescaling once in a few steps, you get a better simulation result. So, now the next thing I want to do now, we now discussed that in simulations, you will be determining a trajectory. What is the meaning of a trajectory? Step 1, step 2, step 3, step 4, all the way up to, let us say, 100 nanoseconds. There will be thousands and thousands of steps. Let us say typically there will be 100,000 steps. So, when I average over all the 100,000 steps, I am going to get only one average, and when I get this one average, I do not know whether it is a good average or not. So, one way to solve the problem would be, suppose I am doing 1 lakh steps. So, I take one set to be 10,000 steps, the one block, next block will be next 10,000 steps. So, this way I generate 10 blocks of 10,000 steps each. So, which means for each block I have a sub average, okay, and the total average will be average of these sub averages. Now, if I know that this is average over 10,000 steps, one sub average, next on the 10,000 steps another sub average. If all these sub averages are very near each other, then I know that it is a converged systems. Okay. So, that means my sub average does not change from one subset to another subset. So, that is one way to confirm that there is convergence. So, if there is no convergence, the first sub average may be x, the next sub average may be 1.1x, the third one will be 1.3x. So, if the sub averages keep on changing, then you know that you have not converged. So, a very good way to check whether there is convergence is to calculate sub averages, then the average over all the sub averages. Okay. So, now this is a typical example of a molecular dynamics. This is just to give you a feel now. What I have done here, I have taken a 3 particle system. So far we have only talked of concepts. Now, let us take a real example. So, in this there are 3 particles, one at the center, one along the y axis, one along the x axis. So, I will calculate. So, this is my initial position. At initial position, the first position is 0 0, second position is 4 0, this is my second particle, third particle is 0 and 4. I calculate the forces on each of these particles using this formula. I calculate the forces using this formula. Of course, these are Lennard-Jones particles, so there are no charges. So, I am just going to calculate the forces now. So, you will see that I have printed the forces now. On the first particle, it is 55, 55, second particle minus 55, 12, third one 12 and minus. That is, on the first particle, both the x and y components are in this direction. Okay. Whereas, on the second particle, the force on the x component is negative and the y component is positive. Whereas, for the third particle, the x component is positive and the y component is negative. See this arrow, this is the direction of the force. So, I calculate the force, use the Worley algorithm and calculate new position. So, I have calculated new position and new velocity. At the new position and velocity, I calculate the force again and I calculate again new position and velocity. Okay. Then again calculate the forces, new position and velocities. So, this really illustrates the use of the Worley algorithm numerically. And an important point I want to make here, what are the units we are using to use in this particular simulation program. Usually we use time in picoseconds, distance in angstroms, this is a standard practice. So, if you use time in picoseconds and distance in angstroms, the force, the units of the force will be 10 joule per mole divided by angstrom. So, I repeat again, if the distance is in angstroms and if the time is in picosecond, energy will come into 10 joules per mole, that is the unit of energy. So, if the energy is in 10 joules per mole, force will be energy per length. Okay. So, my force will be 10 joule per mole per angstrom. So, that is my unit of force. So, it is extremely important to know all the units in your calculation, because if you use a wrong unit, there is no meaning in your result. Okay. So, this is how I have illustrated here a typical example of a molecular dynamics of a 3 particle system. I illustrated 3 steps. You can actually calculate this by hand. Okay. So, make sure you understand everything. Okay. This I have given a Worley algorithm, okay, and I have also calculated velocity using the Worley algorithm. So, now before I conclude, I want to talk about these constraints. What is the meaning of constraints? Suppose I have a molecule like water. As it keeps on moving, the bond lengths and bond angles should not change, because if the bond lengths and bond angles change, the water will become something like a linear water or a right angled water. That is not a realistic water. All water molecules should have the same bond length and same bond angles. So, for that I use an algorithm called a shake algorithm, that is to keep the bond length constraints fixed. I want to fix the bond length and bond angles. So, I will describe in the next class how to use the shake constraints. And basically what we have done, this simulation constitutes an example of a statistical mechanics. So, what is the main purpose of molecular dynamics? The main purpose is to generate a trajectory. So, what is a trajectory? Position and momentum as a function of time, that is called a phase space in statistical mechanics. Okay. And once you generate a trajectory, then you can calculate physical properties as specific averages. Okay. In particular, structural properties can be obtained from spatial correlation functions, that is a radial distribution function, and the time dependent properties, these are the transport coefficients, they can be obtained via time correlation function, that is the velocity autocorrelation function. So, what I shall do in the next class, I will define the radial distribution function as well as the time correlation function. I will describe algorithms to calculate it, and once we describe the algorithms to calculate it, we will also use them to calculate average quantities of lot of interesting properties. So, we have many interesting properties in liquids, and all of them can be obtained as some integrals over either your radial distribution functions or time correlation functions. So, in the next class we will define both these, and we will give the formulae for calculating all the properties, and then give an example of a simulation program. So, once I give an example of a simulation program, so that will complete our discussions on argon. Then we will discuss GROMACS, and once we discuss GROMACS, that will be toward the end of the course. So, you should be able to do MD simulations not only for simple systems, but also rather complicated systems using GROMACS. So, I will conclude my lecture here. In the next lecture, there will be radial distribution functions and velocity autocorrelation functions. Thank you.